Hello everyone, you're welcome to this channel once again. Today we have another question bothering a propeller-driven aircraft. Once again, we have another question on a propeller-driven aircraft and how to calculate the power required at sea level to climb at a flight path angle. Now, let's read through the following question. Consider a propeller-driven aircraft with the following parameters: the CDO, that is the coefficient of drag at zero lift, 0.025, the wingspan 11 meters, the horsepower efficiency factor 0.8, the wing area S 16 meters squared, the weight of the glider of the aircraft 11 kilonewton, the coefficient of lift for the aircraft 0.9, the flight path angle 15 degree. Now let's pull out the parameter one by one. We have a propeller driven aircraft. We're given the CDO 0.025, the wing span 11 meters, horsepower efficiency factor 0.8, the wing area S 16 meters squared, the weight of the propeller aircraft 11 kilonewton, the coefficient of lift for the flight 0.9. We are asked to calculate the power required. Don't let us forget we're given the flight path angle, the gamma 15 degree. Now, how do we calculate the coefficient of drag? Using the formula, let us forget CD. The rate of drag is CD is equal to CDO plus CS squared over pi EAR. And from the look of things, our aspect ratio equals B squared over S, that is 11 squared over 16 will give us 7.56. Now we can slot in our value. Our CD becomes 0.025 plus 0.9 squared over 3.14 times 0.8 times 7.56, which equals 0.06. So our CD equals 0.0676. Don't let us forget that using the fly path diagram representation, we can deduce that this is lift, this becomes a drag, this is thrust, this is the weight of the aircraft acting downward, and that is the angle of fly path angle subtended. Now we can deduce from here that the lift equals weight cos gamma, and from the diagram representation we can deduce that T minus drag, thrust minus drag, equals W sine gamma, and we can also deduce that thrust equals drag plus W sine gamma. So therefore our power required becomes T multiplied by the velocity. So therefore our P will now becomes D to the velocity plus W V sine gamma. Then we know that drag equals the half rho S V square CD. So therefore from here we can deduce that the P, it becomes half rho S V raised to power 3 CD plus W V into V sine gamma. Now going by our resolved equation, we can deduce that lift our P, which is the power required, becomes half rho S V into infinity 3 CD plus W V into infinity sine gamma. So therefore the power required becomes 0.5, 1.25, that is the density at sea level, multiplied by 16 multiplied by the stream velocity, which is the root of 2 W cos gamma over rho SCL. Now, how do we find the velocity? The velocity equals the root of 2W cos gamma over rho SCL, which equals 2 times 11,000 cos 50 over 1.225 times 16 times 0.9 to the root So our V becomes 34.70 meter per second. Now we can now slot in this value into the V. So our equation now becomes, our equation for the power required becomes half times 1.225 times 16 times 34.7 raised to power 3 times 0.0676 plus 11,000 times 3, 34.71 sine 15. Now going with the equation for the power required, our power required becomes 126154.49. So our power required for the propeller-driven aircraft becomes 126.16 kilonewton calculated. Kilowatts. Thank you for staying tuned.